Okay. Okay, so this is the microphone, but it's quite wide, and you will be also the video comes here, so you can move around. Okay, but let's stay around here, not go down there. Okay, and I will check if you are in the field. Okay, sure. Okay. You can check by yourself. Okay. So there is good, perfect. If you come too close, it's not. Yeah. Okay.
Recording in progress.
Do you mind if we record?
Of course, please.
Prova. Okay. Everything is fine. So we can start as well. It's up to you to introduce Mike.
Okay. Okay, thank you for coming. When I started my job, I'd like to.
You have to stay there, otherwise.
I have to
will not-
say that. Okay. Is this good?
Now it's
when I started studying the illusion of life, I came across Mike's books, and book after book, I acquired most of what I know right now, and reading the basis of my research career by Mike's. And even now, I'm glad to say that I'm used to read most of his papers, which is on nature, communication nature, ecology and evolution nature, the main journal and some. It's most of its career is characterized by very important new knowledge and new discoveries regarding the evolution of dinosaurs, evolution of life, and how extinction evolves. I'm very, very glad to introduce to you all Bristol Soap, Mike Benton.
Thank you very much, and thank you for listening to a talk in English. I apologize, ma no parlo. So I'm going to talk about extinctions, and the intention is partly to talk about familiar stuff in geology, but connect to the present day, and to look at the rise of the hypertherm, which is the big new thing. So next, please. And it relates to a book that is just published that I wrote. So next one, please. Of course, one reason that we're all interested in extinction and the public is because of biodiversity. And we know that species do not last forever, and therefore they go extinct naturally. Next, please. And we need to see the role of extinction in the present day first, briefly, before we step back into deeper times. And this slide summarizes current understanding of global biodiversity. The estimates of species numbers have changed over the years. There was a very useful review last year where they gave a total estimate of 10 million species of macroorganisms. That's not including microbes. Next, please. And linked with these understandings of modern biodiversity is the study of conservation, or should I say the study of threats to life. What are the things that we are doing that may speed up extinction occur more than would normally be the case? And again, there was a good review, but I couldn't find one more recently than Monastersky in Nature in 2014. Where he was able to categorize the different kinds of things that human beings do. If you haven't read about this kind of approach, you may think everything humans do is somehow bad for nature. But then we want to know in more detail actually which things that we do are worst and which are less bad. And so in this category, in this study, he divides categories of exploitation, habitat degradation, habitat loss. And in fact, invasive species, this is where you carry cats and rats to other countries, is quite small, 5%. Pollution, according to this, is quite small. So it's actually worth, if you're interested in that, it's a little distant from core geology. Nonetheless, it's worth thinking, and it can be studied that way. And then estimating the rate of extinction is the other aspect that we can look at the present day. And the connection we have, of course, is sometimes people say we're living through the number six mass extinction now, meaning we have 5 big extinctions in the past, is today number 6. The way the estimates are done initially are to look at extinctions we know about, the extinction of the dodo, Raphus ordigus ineptus, and many other birds and mammals are done. We know historically, more or less, which year certain species disappear. They tend to be island species, they tend to be species that lived at low total diversity, low abundance, but nonetheless they can be documented, and therefore you can potentially say from the year 1500 to the present day, these are the numbers of birds or mammals that have disappeared. That can give a way of estimating total loss, because we've got no idea how many species of beetles are dying out today, how many tomorrow, because we don't even know all of the species of beetles anyway. And there are so many that it's impossible to say for sure. So one suggestion has been to take these kinds of figures where we think we know, particularly for mammals, birds, and tropical trees. There is a good inventory of species of all of those, and also quite good documentation of when different species disappear. Next, please. So those kinds of estimates can be scaled to total diversity. I'll go through these fairly quickly because I don't want to labor the point too much. But these have given rise to the sorts of figures that people quote. And these become politically quite important, of course. So if you're interested in this area, it's a good idea to think carefully about the ways in which the data are handled. So if, for example, you estimate that we have lost something like, let's say, 0.2% of birds and mammals per annum, doesn't sound too bad. But of course, that quickly scales up to the total extinction in not a very long span of time. And these are where the figures have come from of a loss of 80 species per day. If we have 10 million species on Earth, we're losing 0.3%, 80 species per day. So that's where that figure comes from, which is often quoted if you see political presentations or read accounts. Next, please. But that's a kind of high-end estimate, certainly up there with mass extinctions. But next, please. That extinction rate is an excessive rate of extinction because, of course, it applies to small population, low abundance species on islands. I won't go too far to see how this works. Next, please. And so the range of extinctions per week is anything from 10 to 690. So the 690, that's the 80 a day. That's the high-end estimate that Al Gore and others used. And the low-end estimate of 10 a week. And you can see how those different figures emerge. And indeed, it's not surprising that we have that range of uncertainty. But another reason, two reasons for mentioning this. Number one, we can connect our paleontological studies to the present day through this way of thinking. And secondly, it's useful to remember that although we don't have fantastic data in paleontology, we are often quite apologetic. We often say, I'm very sorry, the data are not great. This is the present day. The data are not great. And so that we do our best in all cases. Next, please. But what's the next step? What are people doing about it? One of the things people are thinking about is called de-extinction. Should we reverse all of our bad behavior? We've killed all these species. Well, we can bring them all back. Should we bring them all back? Maybe you would like to see the dodo. I certainly would. I think that would be a positive thing. And in fact, the island of Mauritius is empty. There is still a space for them. Nothing else has occupied the space. As for the woolly mammoth, I'm not quite sure. There is a company in Texas called Colossal, and the Colossal company is a deep extinction company, and they're going to bring it back. I think some of you know how they're going to do it. They are not going to. They will do some genetic engineering to make an Asian elephant capable of living. So whether we call that a mammoth, sure. So there is one thing people are doing, and it's great fun, and I love reading what they're planning to do. But I don't know if this is and indeed, people have already reconstructed the mammoth meat. So if you want to know what that's like, apparently you can enjoy that. Next, please. So in the book, I go through a number of the well-known mass extinction events, plus some that are not so well-known. So I'm going to talk about 3 of the well-known ones, which are on different scales of magnitude, and one that is less well-known, and then draw these together in the idea of hyperthermals and how heat is the killer, has been the killer in most of these events. Next, please. So, of course, the end Permian mass extinction 252 million years ago is the big one. And this has been well documented for some time, and you can think about it at different levels, either at the global scale of 95% loss of species, or at the more regional scale, as shown here. So the graph at the top right is from Chinese data. Each of the vertical lines is a species, and there are something like 550 species altogether, and they are plotted according to the line of at which they go extinct. Oh, and so there is extinction happening all the time. And then there are a couple of levels, one here and one here, where extinction is more excessive. And so thanks to and the other way to think about it is in picture form. These are block reconstructions of the seabed based upon the rock and the fossils. And so in the top centimeter of the Permian, this is what you see. A bioclastic limestone full of life with reefs and other organisms swimming above. And then 1 or 2 centimeters above, in the earliest Triassic, you get the after, which is black mudstone, very little life, and a limited number of species living in low oxygen conditions. And so all these different ways of thinking about it all confirm this was a huge crisis at the scale of 95% loss of species. On land, we know the same to be the case. There are well-documented faunas like this one in Russia, but also in South Africa and in China, which show very diverse life, complex ecosystems at the end of the Permian. And at the beginning of the Triassic, most of these groups had disappeared completely. And only 3 or 4 of them survive, including, for example, Lystrosaurus. And another phenomenon of this strange world at the beginning of the Triassic, not only are there very few species, they are cosmopolitan. So any regional aspect that occurred before has been lost for that short time of crisis. Next, please. So a little view of some field work. We used to enjoy visiting Russia. I don't think this would be so possible now. And we could wander about freely doing field work. Here is Moscow, Moskva, Perm here, the origin of the Permian. And this is a distance of 1,000 kilometers. So the Permian Triassic Basin is about 1,500 kilometers from north to south. And the Permian Triassic boundary is highlighted, of course, all the way around here. So Permian is pink, Triassic is blue, and this is the terrestrial PT boundary here. And so as we went with our Russian colleagues, they said, here's the boundary. And this was quite exciting. Next, please. Because it's difficult to document this on land. Here it is. And there's a change in sedimentation at the boundary. Next, please. What's going on is in the Lake Permian is deposition of sandstones and mudstones, and at the very beginning of the Triassic, so here is the boundary, is the conglomerate. And that stands out. This here are people, this is 20, 30 meters of rapidly deposited mass deposition of large-scale debris. Next, please. And all over that Russian base, this is what we've seen. And it was also seen in South Africa. And so here is the summary from South Africa. Before, in the Lake Permian, we have meandering streams, gentle curving streams. And then at the beginning of the Triassic is this switch to coarse deposition and an alluvial fan. So the alluvial fan here is a standard sedimentary facies, well understood in the present day, something you look for in the rock record, indicating mass wash of debris from mountain ranges onto the plain. And this is what was happening in Russia and in South Africa and elsewhere. And in all these areas, the geologists had said maybe local tectonics. At the same time, at the boundary, be interesting to think why would the tectonics just start at that? Rainfall, no. All of the evidence from geochemistry and clay minerals says no, it's getting more arid. And indeed, the suggestion is, I think, loss of vegetation. If you strip the vegetation from the land, then rates of erosion increase massively, 10 times. 20 times. And we see that today. So, next please. And this is detected also in the oceans, where Algeo and Twitchett noted just at the PT boundary a thin layer of silica and organic matter being washed in from the land, uniquely at the boundary. Next, please. And so this is part of the overall story. This diagram will be familiar to some of you, where we have the Siberian Traps eruptions. I've not mentioned that yet, but the leading driver of all of this is massive volcanic eruption. And that generates not only, of course, the lava and rocks and stuff, but has a worldwide effect through the gases. And the sulfur dioxide, carbon dioxide, and methane. Sulfur dioxide in particular, mixing with rainwater, becomes acid rain and causes soil erosion, and that can lead to terrestrial mass extinction. The forests disappear, the plants largely disappear, and disturb landscapes and wash of material into the oceans. And the greenhouse gases, carbon dioxide and methane, of course, lead to global warming and other effects, increased weathering and changes in seawater, acidification of the oceans, and ocean anoxia, marine mass extinction. So all of those boxes are supported by field observations of ecology. And I haven't shown you all of them. I've only shown you the evidence for massive change in the nature of rivers, the topographic change at the boundary. And next, please. The key to this, to killing, is global warming at the center. No, that's fine. So the Siberian Traps, just a quick picture, they're huge. The area covered is, I don't know, half of Europe, half of Poland. It's absolutely. And thousands of cubic kilometers, millions of cubic kilometers of lava. But associated with that are even larger volumes of those gases, just huge amounts. Next, please. And one consequence was that there was global warming of 10 to 15 degrees. So meaning that tropical seas, the Mediterranean and warmer seas, would rise to 40 degrees, which at first sounds okay, but if you know any biology, you know that nothing lives. No plants or animals. And according to the latest geochemistry from Georginsky and others, these high temperatures are indicated at various points, either episodically or continuously through the early middle Triassic. So maybe 5 or 6 million years of high temperatures. And that gave rise to perhaps a tropical deluge zone, as it's called. So this is one of the biggest consequences of any extinction event, lasting for 5 million years or more. And this is still very much understood. Next, please. I'll talk now about a smaller event, an ocean anoxic event, OAE, in the early Jurassic. Next, please. And I'll draw these together later. So near to Bristol, where I work, is a town called Ilminster, and a part of that town has got the lovely name of Strawberry. You can no longer see the quarries there. I've been and looked for them. And these wonderful quarries were operating in the 1850s when fantastic fossils were discovered. Next, please. Mainly three-dimensional fossils with soft tissues of fishes, reptiles, and insects. Here's the head, centimeter scale. Here's the head of a big Pachycornis. Next, please. Here is Charles Moore, who studied these and collected them. Next, please. And many of his collections have not been touched since the 1850s when we started to look at them. Next, please. And he provided a very good section in one of his papers, one of his books, that we were able to use to determine exactly where the fossils came from, and we could re-excavate and check. Indeed, they are Toarcian. They match exactly in age similar fossil beds in Germany, France, other places. Holzmaden is maybe famous. Next, please. And they include lots of insects. This is a marine deposit. Most of these marine deposits of the lattice of the early Jurassic do not include insects, or only very rarely. But in this case, there are insects preserved in the marine sediments. Next, please. So most abundant is Pachycormus at the top. This is a big fish, maybe up to 2 meters in length. Next, please. And small crocodiles. These all seem to be juveniles. The water is shallow. We're near shore. We're getting these insects. We're getting big fish. We're getting small reptiles. Next, please. And some small ichthyosaurs, probably also juveniles. Next, please. And they're beautiful 3D specimens for scanning. For anybody who knows ichthyosaurs, that will immediately look weird. That's a baby. Next, please. And the thin jaw. And so here's the reconstruction. Maybe we made it a bit too near to the shore. The insects flying over and full of these big fish and the reptiles. Probably a breeding nursery for the baby reptiles. The adults would be found to be water. Next, please. And so probably what's going on in the Toarcian is also a hyperthermal, because there were volcanic eruptions at that time. The Karoo Ferrar eruptions in South Africa are the driver of the Toarcian OAE, so it's a hyperthermal. There were extinctions going on, but not on the big scale of mass extinctions. And this event and the other oceanogenic events of the Mesozoic are identified as anoxia events of anoxia and euxinia. And euxinia refers to excess sulfur, and the levels of sulfur kind of dominate in the way that they do in the Black Sea, where the name comes from. And that there is a cycle of excess weathering on land caused by excessive rainfall linked with the rising temperatures, washing various minerals into the shallow water. Organisms can still live on the shelf because of sufficient oxygen, but then their carcasses can get washed off and they can be beautifully preserved because the conditions in the deeper water are so soft tissues survive. And fossils are, the carcasses are not preyed upon, not eaten. And hence Holzmaden and Strawberry Bank are that kind of excellent preservation. And why the insects, I don't know. I've asked people who study Euxinia. The sulfur levels can rise at certain seasons of the year right to the surface and even come up through the surface. So could that kill the insects? Something like that is not impossible. So there's a strange combination here between hyperthermal heating due to volcanic eruption, killing effects of the warming, but also linked with excellent preservation fossils. Next, please. Yeah. So I've got to do the end. I've got to do this one, of course. Next, please. But I'll be brief. But what can you say? You know, the opportunities for artwork are fantastic. A dinosaur and an impact. You could even have a volcano. Did it really happen in June? Yes, yes. Next, please. Of course, you know the classic story and the Gubbio section. Some of you have been there to try and reach the boundary. Of course, it's deep, deep, deep because everybody has taken some clay from that. But you know the story began in Gubbio. Next, please. And the formula by which you calculate the size of the impactor from London. Next, please. And then the evidence that has emerged. Initially, of course, in 1980, they only really had the Iridian anomaly number 1. But since then, of course, so much more evidence has emerged for impact X-rays, including, of course, the crater in Chicxulub in Mexico. Next, please. But what about the Deccan traps? If we are believers in the power of volcanoes to kill, why do we suddenly forget about volcanoes at this point? Well, let's not forget. Let's test between the two. Some of you will know the paper, but there was a key paper 2 years ago that tested this. What would the role of the volcanic eruptions be? The Deccan traps were erupting at the time of the end of Cretaceous, and the impact happened. But let's just think about one thing before we look at the test. If it were the volcanic eruptions, we would expect the extinctions to correspond to a peak of high temperature. If it is the impact of a meteorite, we expect it to correspond to a drop in temperature. Because remember, the Alvarez model is impact of meteorite, a huge amount of dust is thrown up, knocks out the sun, removes sunlight. It's not only dark, it's cold. You get a really sharp, cold spell, very short. Okay, which one? Next, please. So Shelley Hall here did a great paper in Science in 2020, where she and colleagues looked at all the records of temperature, and they removed a lot of poor quality data and focused on the good quality data, which is shown here. And here is the KPG boundary. And what they find is a peak in temperature here, a drop in temperature at the boundary, and then other things going on. So what's happening is the Deccan traps have a peak of eruption at this point, and temperature goes up. And then the impact is right here. And that little V is the impact, the drop in temperature. And so, and the timing, this is 200,000 years before the KPG boundary. So the study is a beautiful one for many reasons. It's a decisive test. That's it. Story finished. We got it. Unless you find mistakes in what you did. But it's about 20 authors. I think they were quite careful. And so this is it. We don't need to debate. The Deccan traps were erupting. They were causing. They were killing. They were doing stuff. But they were not the decisive killers at the end of the Cretaceous. And the other lovely thing, of course, is over the years, we've learned to handle the geochemical data better, that there are better ways of measuring. A lot of older data are now considered to be not so reliable. You don't throw it all in together, or you get an entire span of values at each time point. And so it's a good thing to do what she did, which is to edit the data, remove the poor quality data. And secondly, look at that quality of data, look at that precision of data. Next, please. And June, yes. So many of you will have read these papers last year or the year before, where two papers were published in which studies were made of the gill skeletons of fish. Within these specimens are spherical structures, which are interpreted as melt products of the Chicxulub impact. This is a locality called Tanis in South Dakota. It's maybe, I can't remember, 2,000, 3,000 kilometers from Chicxulub, but within the range of the airborne melt droplets. And we haven't got the full data yet, and I hope we do, because these are supposed to have the chemistry of the Chicxulub impact site, which is not igneous. It is the chemistry of limestone and evaporates. And if that's truly the case, then I think people will definitely believe these really are stragglers, and this is the day the dinosaurs died, the name of the day that we see. And so if this is the day the dinosaurs died, or at least in this case, the fish, these people here did slice through the bones. They calculated the age at which the fish died, they measured the carbon and oxygen isotopes through the growth rates. So they were able to say that this particular specimen died at the age of 1, 2, 3, 4, 5, 6, 7. So 7 and a bit. So this is the inside of the bone, this is the outside. And they're able to track the summer and winter cycles. So summer is high, winter is low. And so the summers are equivalent to these pale colored wide bands when the bone is growing quite fast. And the winter, the cold, is equivalent to these darker bands where the bone is growing much more slowly. How do we know then that well, we know it was 7 years old, but we know also that it was June because you're just getting into the beginning of the summer growth season. And these fish belong to genera that are still alive today, so it's possible. It was June. Next, please. And the universal hypothermal model, I think, is an interesting development that's really been coming together in the field of catastrophe study in the last 20 years. Next, please. And this came from close study of the PETM, which is the most recent of these hypothermal events, where the documentation of dating and temperature and climate change and all these other things has been intensively studied, and that there is good evidence for one of the drivers of rising temperature, which was not only the volcanic activities, the North Atlantic province around Iceland, affecting the United Kingdom and Scandinavia, but also triggering the release of methane from deep oceans. So next, please. Hyperthermals then seem to have occurred many times, maybe end Devonian, end Permian, end Guadalupian, Carnian, I don't have time to talk about that, end Triassic, the OAEs, the PETM, but not the end Cretaceous. That's maybe the only one that is not. Next, please. And so the model is similar to the one we saw for the end Permian, where the driver is volcanic eruption, and is particularly focused on all of the gas emissions coming from the volcano, which can have effects both on the land and on the oceans. Ocean acidification and anoxia, algal blooms, all of these things seem to be standard. And on land, it's more complex because you have acid rain killing plants. You also have other chemical effects, excessive weathering and pouring of various nutrient chemicals into the oceans, but also massive soil and rock erosion happening at the same time as well, which, depending on the scale of it, can have a greater or lesser effect. So it seems that this, so LIP is large igneous province. It seems that this kind of hypothermal model is maybe responsible for 15 or more geological crises. The KT event is different. We know that. We're not sure about the older things like the end Ordovician and end Cambrian and other older events. There are other models for those. Some of them might even be hypothermal. Sure. Next, please. But why does it matter? This is my last section to try and explain the biology of a hyperthermal. The geology of it, I think, is fantastic because it draws upon nearly every branch of geology. Classic geology contributes to all aspects of what we think we know about it. But what about living organisms? So there's been a long history of the study of the physiology of plants and animals, particularly marine plants, including at the Marine Oceanographic Station here in Edinburgh. And the different kinds of killers are listed here, relating to high temperature in one way or another. But I think the key one is high temperature. People have tried to argue the case for the other factors as killers, but I think it's much less convincing. So next, please. First of all, hypoxia has been proposed, the low oxygen levels, that there was a drop in oxygen levels at the end of the Permian. And indeed, it's known that different groups of marine organisms have different abilities to survive in conditions of low oxygen. and foraminifera at this end, and crustacea at the other end. And so the degree of sensitivity varies. It doesn't really kill them. They're all capable of surviving or moving away. And so foraminifera on the left-hand side are most resilient. That means they are least affected by reductions in oxygen, whereas crustaceans at the right-hand end are most affected. But the hypoxia thing on land as well, people have argued. But of course, if you think about people moving from sea level here, Mexico City or Tibet, you can adapt. You can survive. Next, please. Hypercapnia is much more convincing as a killer in the oceans. This is high levels of carbon. And in a classic paper by Andy Knoll and colleagues, they gave a fantastically clear proposal based on knowledge of living marine invertebrates and their ability to survive acidification. Really important, not only for the present day, where oceans are becoming acidic. We need to know who will survive and who will not survive, but also important for these hyperthermals, because all of the hyperthermals involve ocean acidification. And there is a very clear prediction from this that poorly buffered or highly calcified taxa, corals, sponges, brachiopods, etc., all of those organisms that build a skeleton from aragonite, they are vulnerable. And the more buffered taxa, meaning they can survive the osmotic stress, regularians, gastropods, bivalves, crustaceans, fishes. So yes, hypercapnia, massively important. But normally acidification comes with rising temperatures. Oh, next please. So heat stress is a well-known phenomenon that, of course, all organisms have a preferred temperature range that they prefer to live at. And if they are if they are pushed into hotter temperatures particularly, they get stressed like this unfortunate pig. And in fact, a lot of the studies in this area have been purely for economic reasons, because people want to know how to get fatter pigs, how to look after livestock and fish farms and all kinds of things, what temperature is ideal. But one aspect of heat stress is a simple observation that as temperature rises, the demand for oxygen increases. So if, as through some of these hypothermals, temperature is rising and oxygen is falling, that's a perfect storm. That's the sort of, it's going the wrong way. And it's particularly the rising temperature drives the need more oxygen, but they can't get it. Next, please. There is an upper thermal limit. So eventually, of course, plants and animals will simply die if the temperature is raised to a certain level. But again, in this, a very useful review paper by Sun et al. In 2014 in Scientific Reports, they presented that earlier graph, and here are plots of the upper thermal limit for radiolarians and ostracods. So remarkably, some ostracods can survive up to 50 degrees or 55 degrees. And some hot spring ostracods, they're obviously specially adapted to live in different conditions. But clearly the majority of marine organisms will not survive beyond 35 degrees. So remember those kinds of increments of temperature from 25 plus 10 plus 15. So at the end of the Permian, at other times, temperatures were going up to 35 or more. So organisms would not be happy. Next, please. On land, aridity is clearly important, and at the end of the Permian and at other times, there is no question. And we see it today as deserts are enlarging. The area available for life becomes small. This is happening. They can either die or live. But this is probably not the biggest killer of all, because it just applies to a part of a region of the world. Next, please. Acid rain and mass wasting, I've talked about that quite a bit. We're well aware of acid rain today. We're well aware of one of the effects, that it can kill the trees eventually die, and as their roots loosen, the soil will be washed away, and particularly if they are on a hill, the water and the sediment just disappears. And what was a flourishing forest becomes bare, and it takes a long time for that to recover. Soils can disappear in a week, but it might take thousands of years to exit. Wildfires, a lot of the events, including the end Cretaceous, possibly the end Permian, were associated with wildfire. That would have a dramatic effect. The TV filmmakers like that because they can show it. But remember, this is not much of a long-lasting effect, actually, on land. Wildfires happen, we've seen them this year. They're very distressing, but they don't have a long-term impact like recoveries. So not a key killer. Next, please. So I think out of all of these, I've summarized which would be the key killing agencies. All of these physical effects, physical crises come as part of the hyperthermal package. The reason we see them today is, of course, we are generating a hydrothermal, and it involves all of these different factors, and it has predictable course and a predictable series of effects. And this is a nice observation. It's a pity to offer this, of course, to offer ourselves, earth scientists, as useful in talking about catastrophe. But nonetheless, we don't have to speculate. We don't have to guess what is going to happen because these events have happened in the past. And if you accept that maybe 15 of these crises in the past are hydrothermals, that they share a great deal of the model that drives them, and therefore, and likewise, the consequences for life. This means we have a menu of past experiments that have happened. And if anybody wants to know what happens if temperature goes up by 2 degrees or 5 degrees or 10 degrees, we could say, well, we don't have to speculate. We can actually go to examples in the past. Which one should we choose? Say, this is what could happen. And I think the combination of studies of modern plants and animals and linking that with really quite high quality data now coming from ancient studies of these ancient events means we've got a much richer understanding of what was going on in the past and how that connects with the present day than we might have had before. Next, please. So there we are. I regret there is no Italian translation yet, but we're working on that. So the book is only just come out. The themes I've talked about in the lecture are covered there, but also you don't need to buy the book because this is just the current literature. It's all out there. You can read all of this as well. So thank you for your attention.
Question first, we take questions from the room, and then we will open the question to the audience online. We have 30 people online, some 50 more of YouTube, and one of you can only chat, not speak with us. So please, don't be shy. Yeah.
The extinction in the Triassic of
So the question we have to repeat because probably yes. So the question is about the extinction at the end of Triassic, the Triassic-Jurassic boundary extinction.
So it is one of the hypothermals. It's driven by the Central Atlantic magmatic province, and of course that was the beginning of the opening of the Atlantic, those eruptions. And I think the same kinds of consequences of rising temperature, maybe only about 5 or 6 degrees at that time. But I think otherwise the model is the same. The only other point about that is, though, it did seem to start early. There were earlier events. And we're studying some aspects of this where there's a great deal of uncertainty about the duration of the region. Just a little bit of special knowledge, but could be anything. So the last stratigraphic stage of the Triassic could according to the official timescale, is 80 million years. According to some people, is 500 million. So it's quite a variation. And the 500,000 is important, if that's the truth, because there are a number of isotopic anomalies in quite serious extinction before the TJ boundary.
Analog over there. Please.
Which of the past exchanges would you say is the best example for the extinction that's going on today?
So the question is, which of the past extinctions would be the best model for the extinctions today? That's a great question, and I can't answer it because I think I guess what I would say is all of the past events have something to offer, because if we see them all as following the same model, then in a way we have to decide what is happening today. What is our temperature? So we think we're going to go to +5 degrees, that may be the end of Triassic would be a good example. If we think we're going to go to +3 degrees, that may be the end of the other. Let's hope we're not going.
The normal rate of extinction that nowadays is going on because of human activities. It is expected for biodiversity to eventually recover, and it could be so brave and so heavy to never recover like before.
Okay. So the question is about the present day and about recovery of life. How does life recover? I think the lesson we learned from all of these past extinctions is life always recovers. Of course, it's here. And if it did not recover, we would. So it does recover. But what people forget, of course, often is the time scale of recovery. So recovery after impact is much quicker than recovery after hypothermia. So recovery after the end Cretaceous event is really very quick. It really got going within tens of thousands of years, more or less done, about 50,000 or 100,000. Whereas we saw for the Permian, it took maybe 5 years. Continuing ice temperatures and so on. And I think the hypothermals maybe, it's because I suppose the impact is just a single event. That's it, it's done. Whereas with the hypothermals, it's never just a clean single event. It seems to be this later bits of eruptions, temperatures rising. But of course, the time scale still, even with those quick recoveries, is not on the scale of human lifetimes. And so we would like to think if we can control the rising temperatures today, that when you're all my age, you'll be able to see life flourishing today. All species. It probably wouldn't happen as quickly.
So eventually we'll recover at previous levels, right?
Yeah, life always recovers. Whether to previous levels, often it goes higher. You know, that's another thing that we think about, paleontologists think about, mass extinctions. I haven't talked about this. Looking back, they've all had a positive aspect, but that's because we appreciate modern biodiversity, including ourselves. And of course, it's well known, and it's the truth. If the end Cretaceous event had not happened and dinosaurs had not been killed, they probably would have eventually died because temperatures rose. So, but they would have died later. And so whether primates, different groups of animals were involved, I'll say. And obviously the end Permian event had a massively influential effect on entirely redesigned ecosystems. The whole of the Earth just looked so different. It became kind of modern, higher energy than it had been. So life altering.
Question from the room? Any question from the audience online, from the people connected to Zoom? If you wish to ask a question, just open your microphone, tell your name, and ask your question. No question from the audience? They are all shy. Oops. Any other question from here? Okay, I will ask a question. I've been studying the But some of the events, at least the Phanerozoic events, I started with the Cenomania Juronium, that is a very small event, and then I went to the Appia, so I started with the Anoxia, and then I went to the Toasha, and then last PhD thesis that I tutored was about the N-Trias extinction, always in shallow water, carbonate lab, shallow water form. And well, the idea is that they are all perturbers, but if I look at least at these 4 events, they are all different. They seem to be all different in some way.
Yes.
One is more nutrients, the other is more acidification. So how can we get with different, let's say, detail of the selectivity of extinction, for instance, if we start with the same forces that we saw with the virus?
So the question is about the fact that, of course, as you're absolutely right, when you look in detail at different fascies, different regions, you see different effects of what's going on during these crises. I guess I've just been generalizing at the global scale and missing the fine scale detail. But I don't know whether there are differences. Could you have, I guess, through different times, you can have different fascies because of different kinds of groups of organisms at the time, how that could become, in a sense, predictable. Because obviously you're documenting exactly what's occurring. Connect all of that together, and why would it be different?
And do you feel that, I mean, let's say the Earth is becoming more resistant, more resilient or not?
Interesting. Is the Earth becoming more resilient or not? And whether we, and also whether there is any other kind of change. Some people might refer to Gaia and talk about some other kinds of Earth life changes that are directional. It would only occur through the Gaia life. Just organisms can organisms through time have different effects. So there's others. But whether it means that the Earth is getting more resilient.
And what I mean is, if you look at the carbon system, when we get just carbon depositing in shallow water, of course, it was much easier.
Yes,
But that will acidify the ocean.
yes.
When we get down deep in the ocean, of course, we have a buffer.
Yes.
So in this sense,
That's really brilliant. You're absolutely right. In the Jurassic, that's right. Yes. We need an Earth ocean model.
there is a couple of days ago with the model, in general model connector that Benjamin Mills has.
Okay.
I saw it. Some of this. Thank you. Any other questions from here? If not, you will say a few words.
Besides saying, Mike, thank you. Wolfgang, thank you. I think that most people is actually impressed by talking about extinction, because we're running. I guess I am honest. As that there are very big difference for what is occurring nowadays as compared to any other mass extinction. I take for granted that we are going through a mass extinction. And there are some aspects that really differ in terms of time. For instance, periodic homogenization, one of them. In this case, the homogenization is preceding extinction event, or even contemporary to the extinction. And that's kind of, say, a positive feedback on extinction rate. And this is, in my personal opinion, I have to study it. It's a long-term wish. I think that one of the reasons why it is growing so fast that we can actually measure after the human lifespan, is exactly because there are positive feedback. I wish to know about it.
I'm very happy to hear you talk about it, and I have no personal anything on that at all. And could you, I have to throw a question back, could you do a comparison with any of the past events?
I don't.
Yeah, okay, yeah. Because some of